Hi everyone, my name is Tin Junming, together with Rizwan, Natasha, Rusni and Kawei to do this poster. Our topic is cone penetration test. This test follows the standard of ASTM D5778. This test provides a continuous profile which helps to identify the soil layers. It measures the tip resistance and side friction, enable us to determine the soil behavior type by those values. There are variant or new features from this test: piezo cone, which measure the pore water pressure, and seismic cone that contribute to liquefaction analysis. This CPT is performed using a large truck molten rig. Smaller trucks are available for sites that cannot be accessed by a large truck. The truck has a jet system that pushes the probe to penetrate the soil layers. The common size used for the probe is 10 and 15 mm square. It consists of three main components, which is the 60-degree conical tip that measure the end bearing load, the friction sleeve that measure the side friction, and pore pressure transducer that measure the pore water pressure. For seismic cone, there was 3 axis geophones installed in the probe to capture the seismic wave. Procedure for the test: first, choose the test location and set up the CPT equipment, which is the truck and the probe. The cone was pushed to penetrate the soil layers at a rate of 10 to 20 mm per second until the desired depth or until the refusal point, which is when further penetration is not possible. The tip resistance, side friction, and pore pressure were recorded continuously in the computer. So we can use this data to understand the soil behavior type and their engineering properties. For seismic cone, the procedure almost same. The only difference is the probe will stop when penetrate until a certain depth, and the shear wave is generated at the ground surface by hitting the truck supports or by other alternatives. The geophone will receive the waves and obtain the values for wave velocity at that point. The process was repeated at different depths, and finally we will get a plot of shear wave against depth. This is the basic equation to get the values of tip resistance, side friction, and friction ratio. The computer will record these values automatically, so we can directly use those numbers to predict the soil type. For example, for this diagram, the upper part have higher value of tip resistance and lower friction ratio. So from the chart, we can say this soil layer is gravelly sand to sand. And for lower part, which has low tip resistance and higher friction ratio, is silty clay to clay. Here are some correlation from recent studies. I will show some of it in example questions later. First question: in a deposit of normally consolidated dry sand, a cone penetration test was conducted. And this is the results. Assume the dry unit weight of sand is 16 kN per meter square. Estimate the friction angle and relative density of the sand. For part A, we can do a table to calculate the friction angle at each depth and get the average value. For part B, from the tip resistance, QC, and effective stress, we can draw two lines in the chart to estimate the relative density. So the final answer is friction angle 39.8 degree and relative density equals to 58%. Next question: a cone penetration test was performed within a proposed project site. The tip resistance and sleeve resistance of 1000 kPa and 35 kPa were recorded respectively at 9 meter below the ground surface. It was found that the top 5 meter loose clayey sand is underlain by other material having unit weights of 17 and 18.5 kN per meter cube respectively. Assume the groundwater table is far below the ground surface. Determine the soil type and the undrained shear strength. So the diagram look like this. First, we calculate the friction ratio, which is 3.5%, and with cone resistance of 1 MPa, we can estimate the soil as 9 meter below the ground surface, could be silty clay or clayey silt. Next, we calculate for the effective overburden, which is 159 kN per meter square, and we can calculate the undrained shear strength by the equation QC minus the effective overburden divided by NK, which is 15 given in the question. So the final answer is 56 kN per meter square. For conclusion, no boreholes required in this cone penetration test. It is faster and cheaper compared to drilling and sampling. It provides more consistent and reliable results than standard penetration end values. But there is also shortcoming for this test, which is no soil samples for further analysis, and it is unsuitable for gravelly and rocky materials. Thank you.